So in this video, I'm going to talk about the details of how a NAT operates, and that is the rules and recommendations that are given in terms of NAT behavior for handling both incoming and outgoing connections, possible packets that traverse, as well as how a NAT responds when it's not acting as a NAT. So recall that a NAT, a network address translation box, will set up mappings from internal IP address port pairs for a transport protocol to external IP address port pairs. So here we have a NAT whose external IP address is 128.34.22.8. And so it has an internal interface and an external interface. To the external world, this NAT appears as 128.34.22.8. To the internal world, it has another IP address, say 10.0.0.1. Now, host A can, by sending a TCP connection open, a SYN message to server S on port 80. The NAT will observe that, will translate host A's internal address and port 10.0.0.101.45.12 to the external address and port 128.34.22.8. And it's going to assign an external port, in this case 6641, for this mapping. And I'll set up this mapping. So one question you can ask is that if some arbitrary packet comes into the NAT, how should the NAT respond? So now, if the NAT starts receiving TCP packets from 128.34.22.8, packets to 128.34.22.8 port 6641, it should translate them. That's what the mapping says. Now, it might have restrictions on that based on whether it's full cone, port restricted, etc. But generally speaking, packets which match this will traverse. But what happens if it receives a packet destined to its external address, so 128.34.22.8, and port some random port of 55,127? What should the NAT do? Well, in the end, the NAT is itself an IP device. And the fact that some of its ports happen to result in translation is independent of the fact that how it would respond. So imagine that there were no port mapping set up, that there were no internal nodes to the NAT, that nobody had opened any connections. How would the NAT respond if you tried to open a connection to it? In this case, it would respond as it always would. So for this particular case, it might do a connection refuse, like a reset packet, or depending on what packet comes in, it could send an ICMP error. And so generally speaking, the NAT behaves like a normal IP device or an IP router, with the exception of when packets come to the external interface that have a mapping, or when packets traverse from the internal interface and generate a mapping. So besides that, if you had no such A or B or any node behind it, then that behaves just like a normal IP device. So for example, many NATs, such as your home router, in fact run a web server on port 80. So if you have a home wireless router, it runs a web server on port 80, which is what lets you configure it. Or sometimes it's not port 80, but some other port. But the idea is that the NAT itself can respond to connections, whether they be for a web management interface or for other services. That's a perfectly reasonable and allowed behavior. So one question that comes up when you have a NAT is what causes you to set up these mappings? So you can imagine in the case of UDP, this is generally when a packet comes from the internal interface going to something external. The NAT sets up a mapping that IP address port to an external IP address port. Of course, the NAT needs to be careful about these allocations so that it's not reusing them. TCP. Well, if you see a TCP SYN, then you know to set up a mapping, or you could even be a little more liberal and say, look, if we see any TCP packets coming from inside, then we assume there should be a mapping and just set up the mapping. There's of course a question then, so this is how you create mappings. When do you tear them down? Well, UDP, since there is no control sequence, generally these are on a timeout. Mappings are torn down on a timeout. You do need to reclaim them, otherwise you could run out of external ports to use. TCP, well, if you see a proper FIN ACK exchange to tear down the connection, then you know that you can garbage collect the connection state, the mapping, a little more quickly. Of course, there are some edge cases here. You need to be sure it actually was discarded. You want to make sure that you don't enter some state where it's possible to lose data. So it turns out that there are RFCs that go into detail on exactly how NAT should behave. And these behavioral recommendations came out after almost a decade of experience with these devices and how they can possibly disrupt applications through strange behavior. So there were some early documents that tried to state, based on somebody went out, actually Cullen Jennings went out basically to Fry's Electronics and bought 25 different NAT boxes and just measured them and saw what they did, and they did all kinds of crazy things. So based on that and based on application behavior, the IETF came up with a pair of recommendations, one for UDP, one for TCP. There's also for other behavioral recommendations on how NAT should behave. So UDP is specified in RFC 4787. So here's RFC 4787. As you can see, it's a best common practices, number 127, best current practice. And so, generally speaking, these documents have serious list of terminology. They have a set of behavioral recommendations. So here, for example, is recommendation 1 or requirement 1. A NAT must have an endpoint independent mapping behavior. So what this means is that if we return to the terminology used to describe NATs, what this essentially is saying in terms of that classification terminology, if you were to read through the details of the document, is that NATs cannot be symmetric, in that the mapping a NAT creates for UDP between an internal IP address port and an external IP address port must be independent of what the endpoint is. It can't be a symmetric NAT where it sets up a new mapping for every external IP address and port, because of all the ways in that tends to break applications. So here's a second recommendation. Here's a recommendation that NATs have an IP address pooling behavior of paired. So this is for NATs that happen to actually have multiple external addresses. And the idea is that, hey, if we can, then UDP packets coming from the same internal IP address should appear to have the same external IP address. So here's the third sort of recommendation, that requirement, which has to do with how ports are assigned. So it turns out historically, ports 0 to 1023 were considered system services. So these were ports which only administrators or super users could bind to, basically root on Unix systems. So that's why you see things like HTTP, SMTP, they're all running on these low port numbers, as opposed to lots of application stuff like BitTorrent or Skype, which run on high port numbers. And so that's this historical artifact, but there are some sort of assumptions that applications have made historically based on this. And so what one of this requirements says is just to kind of, so we don't break things, that if the internal port is between 0 and 1023, then the external port should be between 0 and 1023. And the opposite is also true, that if it's not, if it's in 1024.65, 65535, then the external should be between 65535. So I'm not going to go through all of these requirements. But what's nice actually is if you read through these documents, is it really gives you a sense of all of the different kinds of application expectations that there are. What's nice is that there are these justifications. They'll even explain, like, hey, there are applications that make these assumptions, or protocols that make these assumptions, and therefore the NAT needs to do this so it doesn't break those applications. It gives you just this nice sort of a couple of points of interesting protocol approaches that happen on the internet. Now, the TCP requirements are specified in RFC 5382. So we can see the first requirement for TCP NAT behavior is very similar to UDP, this endpoint independent mapping. Symmetric NATs are really bad. They break all kinds of things, so never build a symmetric NAT. So that's requirement number 1. But unlike UDP, TCP has connections, and connections set up. And so there are a couple of requirements that come out for TCP that aren't present in UDP. For example, and this one's kind of interesting, is requirement 2. A NAT must support all valid sequences of TCP packets for connections initiated both internally as well as externally when the connection is permitted by the NAT. And the basic point here is this subpoint A, that a NAT must handle TCP simultaneous open. So this gets back to the case we talked about NAT hole punching, where it can be that two nodes behind NATs, say A and B, they want to open connections to one another. They want to open a connection through the NAT. So what they do is they talk to some external server, and there are servers that provide this abstraction, things like ICE, that allow them basically to do some query responses to figure out what kind of NAT they're behind, also to figure out what the external IP address and port is associated with their local IP address and port. So based on this, both A and B can figure out, given their internal address and port, what's the external address and port. They somehow exchange this information through a rendezvous service, and then both A and B simultaneously try to open TCP connections to one another. Now, it could be that these connections are there, or the state is there. But the basic point is that it can very well be that B sends a SYN, which sets up the state, and that SYN reaches A before A has set up its translation state, and so the SYN is not going to traverse. However, the state now exists on B, so B now has a translation entry. Now A then opens up a connection back, and its SYN does traverse this translation, and now A can open a connection on B. But the thing is that this is a simultaneous open. B has sent a SYN, and the SYN is outstanding. In terms of the TCP state diagram, it's already sent a SYN. This is the simultaneous open, when A and B send SYNs to each other at the same time. So for peer-to-peer applications where A and B want to open a connection directly to one another, it's important that a NAT allow this kind of TCP open. That it's not just that, we don't support simultaneous open, and so therefore we're not going to allow this SYN to traverse because that's an incoming SYN. That if you have a mapping, the incoming SYN must be able to traverse. So that's what here requirement 2 is saying. But even more generally, it's saying that, look, TCP has a state diagram, and that you're supposed to be able to traverse the state diagram to open a connection in any way that you want, and a NAT should not restrict that. That is, that NAT should not be somehow limit the TCP implementation options. So here, requirement 3 states that it should have an endpoint independent filtering behavior. So this is back to the terminology talked about in terms of classification of NATs. This means a full cone NAT. That it's recommended that NATs, in terms of TCP, be full cone. And again, like the UDP recommendations, each of these behavioral recommendations, each of these has a justification. And so it can be really sort of very, very sort of insightful and illuminating to read through what are the kinds of applications, what are the sort of the edge cases that can make the NATs can break. And you see a lot of them relate to peer-to-peer, in particular voice over IP, all those kinds of applications where NATs work fine when simply you have a client behind the NAT opening a connection to a server. But anything peer-to-peer where things behind NATs want to open connections to one another, you have to have an intelligent behavior in the NAT, otherwise you can break those applications. So this one, requirement 4, is kind of an interesting edge case, which is that so a NAT must not respond to an unsolicited inbound SYN for at least 6 seconds. So here's the case why this is important. Again, let's go to this example where we have A and B that are both behind NATs, and they're trying to do a simultaneous open. Now, it turns out that A ends up sending its simultaneous open well before B does, such that its SYN arrives before B has tried to open its connection to A. So if B's NAT responds to this unsolicited inbound SYN by saying, sorry, connection refused, or by saying an ICMP error, or whatever it wants to do, depending on the circumstances. The problem then is that this might come back to the NAT and cause the NAT to tear down the state. And then when B tries to do its own simultaneous open, so here would be the error. If B tries to do its own simultaneous open, that state is now torn down, and that's going to fail. And so the idea here is that if B has to wait at least 6 seconds, the assumption is that B and A, if they're doing a simultaneous open, are going to try to do so within 6 seconds of each other. That's what it sort of means, simultaneously. And so the NAT will wait before issuing that response such that B has a chance to do its own open, which could then set up the state for A. Note then in the second sentence, if during this interval the NAT receives and translates an outbound SYN, it must silently drop the original unsolicited inbound SYN. So in this case, inbound SYN came in, it was unsolicited, but then suddenly something showed that maybe it was solicited. You should just drop it. You shouldn't issue an error. You can ask the question as to whether or not you should have it traverse the NAT. That would be another approach. I actually went back and looked through some of the archives, and this just seemed to work pretty well. The mailing list archives about this discussion, this seemed to work pretty well. It means the NAT doesn't have to buffer these SYNs. It solves the problem and sort of is the least complicated answer. So that's just a brief overview of kind of some of the internals of NATs and their policies and the algorithms that they use and some of the rules that there are for their behavior to allow applications to work. If this is something that's interesting, I totally recommend reading these RFCs in a bit more detail, especially because they give these really nice descriptions as to why these behaviors exist, particularly for peer-to-peer applications.